Hi, this is Professor Fernandez, and in this video we're going to work out an example on the interval of convergence of a power series. This example comes from lesson 11 in this Calculus 2 course. You can access the notes for that lesson at this website, and you'll find these other resources there as well. Let me mention first and foremost that this is about the interval of convergence of a power series. So in the video that preceded this one in this playlist, video 11.1, I do a pretty extensive review at the beginning of the video of both power series and this notion of an interval of convergence and its related notion of a radius of convergence. So check out that video if you want a review of all that stuff. I'm going to just assume that you're pretty comfortable with all those notions and then jump in here to find the interval of convergence. Okay, so this example says find the interval of convergence of this power series. And remember what this means. This means the set of x values such that when we plug it into this power series, we get a convergent a convergent infinite series. Could be geometric, right? We don't know. But to find that interval of convergence, like we talked about in the video before this, 11.1, we usually use the ratio test, right? So let's go ahead and apply the ratio test here. The ratio test was covered itself in an earlier video. I'd like to say maybe the videos in lesson 10, maybe lesson 9. Just look around the playlist, you'll find them. So for the ratio test, as I suggested in those videos, we'll take the entire expression that you're taking the sum of as your a sub n. So in this case, a sub n will take as x to the n over n. A sub n plus 1 is replace all the n's there with n plus 1. There we go. And then from these, we form the ratio of these successive terms. So it's this divided by this. So we're going to multiply by the reciprocal n over x to the n. You can see that because x to the n plus 1 is x to the n times x to the first, this x to the n cancels with that one. So we're left here with x times, and then I'm going to just group these into their own fraction, n over n plus 1. Now, in the ratio test, right, we look at the limit of the absolute value of the ratio of successive terms. So I'm going to take the absolute value of this. There we go. There we go. And then just notice that the only thing here that could be negative is the x, right? So that's absolute value of x times n over n plus 1. This term does not have absolute values because look at the range here for n. Let me erase this. So n goes from 1 all the way to infinity. So all these n values are positive. N over n plus 1 is a positive fraction. So this is the only thing that keeps the absolute values. Okay, and then finally for the ratio test, take the limit as n goes to infinity of this, which is equal to this. So we just plop that in here. And we're left calculating the limit of this. And like we've talked about in those previous videos, because we're thinking of x here as a fixed number, right? We don't know yet how big or how small. That's part of the idea of finding the interval of convergence. Anyway, x is not depending on n. So this absolute value of x term comes outside of the limit. And then we are just left calculating this limit. This is a calculation that we've dealt with before in the course. So I'll send you to various places. In video 5.2, we talked about how to calculate limits as n goes to infinity without using L'Hopital's rule. I believe in maybe the videos for lesson 8 or 7, we talked about using L'Hopital's rule. So there's a variety of ways you could calculate this limit, but long story short, I'll do the growth argument. So as n gets larger and larger, going off to infinity, n is much, much bigger than 1, right? So we can effectively ignore the 1 because this rational function is going to look very much like n over n as n gets really, really close to infinity, or it just gets infinitely bigger. So n divided by n, that's 1. So therefore, this limit is 1. And multiplied by absolute value of x, we get absolute value of x. So that is the result of the limit. This limit equals absolute value of x. Now we have to go back and remember the ratio test, right? The ratio test says that whatever you get from this limit as n goes to infinity of the absolute value or ratio of successive terms, if it's less than 1, then the power series converges. So we want this to be less than 1, absolute value of x to be less than 1 to get convergence. And that I would call is sort of our smallest possible interval of convergence. So this could be the answer to the example. Find the interval of convergence of this power series. It could be the answer, but we need to investigate now the endpoints, right? So one thing you want to do is you want to, unravel this inequality. So this is the same as x less than 1 and greater than -1. And then now we see that at the two endpoints, where x equals 1 and where x equals -1, now I have to go back and investigate convergence separately for those two endpoints. So that's what I'm going to do next. And then, that process will tell me that it either converges at one, both, or neither. And then I'll be able to say confidently, based on those results, this is the interval of convergence, whatever it is. Okay, so this is part of the process where really everything that we've done so far in the course, this is lesson 11, really comes back to help. All the convergence tests from infinite series, they might show up at this stage of the process. Because check out what's going to happen. If I take x equals 1, substitute it in there, the power series becomes now an honest-to-goodness infinite series. What I mean by that is an infinite series of numbers, right? No longer have, there's no longer a power series, sum of powers of x. So this particular infinite series we're left with, we know a lot about. You might recognize it right away, but I'll just remind you that this is a very particular type of P series. Those are series that look like that. And we know that if P is greater than 1, you get convergence here. If P is less than or equal to 1, you get divergence. Okay. So that gives us information about, we're recalling information about P series here. I'd like to say that that was covered maybe around lesson 6. So take a look at the videos for that. You might also recognize this as a very special series, right? This is called the harmonic series. Either way you recognize it, it turns out that this series diverges. Whether based off of this and the fact that here we're looking at n to the first, so P here is 1, or based on the fact that you might have studied the harmonic series as a separate kind of special case of one of the first types of divergent series you ran into. So conclusion, over here on the right-hand side, at x equals 1, the series does not converge. So we have to exclude x equals 1 from our interval of convergence. Okay, let's go off and see what happens if x is -1. So let's put -1 here. So what that's going to do here, you see the x to the n, I'm going to replace it with -1 to the n. -1 to the n. You can see that that's going to change everything. This is no longer a P series, because the terms are not all positive. In a P series, all the terms are positive, or all the terms are negative, if it's like -1 over n. This is a series that alternates. So this is an alternating series. And actually, it's the alternating harmonic series. So alternating harmonic series. Again, you may already know whether this converges or diverges, but I'm just going to send you off to a certain portion of this playlist, particularly in lesson 8, to take a look at some of the videos that we talked about there for how you might actually show that this, in this case, turns out to converge. And what really happens here is the easiest way to do this is by using the alternating series test. So, long story short, right, that involves making sure that the successive terms are getting smaller in magnitude, where the a sub n's are picked out from here, or you might run into the alternating series looking like that, right? So, going back to the series we have, a sub n would be 1 over n. And certainly these terms, that's a really terrible 1 over n, sorry. Certainly these terms satisfy this condition. You think about like 1/2, 1/3, 1/4, right? So successive terms, 0.25, are getting smaller, 0.33 and 0.3, and this is 0.5. So as you move forward, the terms are getting smaller, so it satisfies that condition. And then there's a limit condition and a couple of other things that I want to send you to these videos if you've forgotten, but you apply all of these, right, to this series, which again is the alternating harmonic series, and you're able to determine by the alternating series test that this series converges. Okay, so going back here to the right-hand side, we now have checked that at x equals -1 it converges. at x equals 1, it does not converge. So if I had to then give a final answer to the question posed, what is the interval of convergence, then the final answer would be including -1, because it's an alternating harmonic series there, all the way up to 1, but excluding that, because then it's the harmonic series. You might see this sometimes in number line form, right? So include -1 and exclude 1. And then so every x value in here that you want to plug in, this interval is centered at 0. Every x value in here that you plug into this power series yields an infinite series that converges. Anything out here, or out here, right, yields an infinite series that diverges. So that's really the full answer to this interval of convergence. A couple of things I just want to end the video with. Remember, if we zoom back, how did we do this? We used the ratio test to get the smallest interval of convergence. And what is that? That's always going to have the form x minus c less than r. That goes back to a theorem I had talked about in video 11.1. So check that out. So I say smallest because, again, as what happened in this example, the next thing you need to do is you need to investigate the endpoints of this interval you got in this first step. Let's call this step 1, step 2. That's what we did here when we looked at x equals 1 and x equals -1. Once you investigate those endpoints, then your full, step number 3, full interval of convergence will be x minus c less than r, the original interval you got, -1 to 1 in this case, plus x equals, I'll just put question mark here, right? Maybe the right endpoint, maybe the left endpoint, maybe both, maybe neither, right? But the idea is that you now have this procedure that you can follow, and it's not as simple as just the first 2 steps. The first 2 steps are really just, the first step. It's not as simple as just applying the ratio test to get this preliminary interval of convergence. You really have to investigate the endpoints. Great, thanks for watching.